So let's get a couple of words and look at generally how a system like this might work. Up at the top, what might be a typical serial setup where we have two different, let's say Arduinos, that both want to send, that would be transmit, which we abbreviate TX, I don't know why there's an X in there, and receive, we abbreviate that RX. There's always going to be a common ground, so we don't have to worry about that and we won't be showing it anymore. So in general, we're going to need two wires. You saw the clock and the data on the last system. Here's a little bit different way of using those two wires. And all different serial formats are going to somehow try to minimize the number of wires, because that's expensive stuff, and yet give you a lot of flexibility in how you get data from one place to another. But in general, you're going to do something very like this with your Arduino. Each time we want to send data, we're going to send what you might call a frame. Sometimes this will be referred to as a packet. It's going to be a chunk of information, which is not just the data you want to send. It turns out you need to send a little bit more, in fact, in some cases quite a bit more, to get the data across. And here you see in the middle of this frame, it says data. That's the thing that you really want to get across. But there's some header and footer, some stuff wrapped around it. There might be something that says, hey, data's about to start. And in this case, that's a single bit that's shown. That might synchronize the two channels. It might say which channel, which receiver is going to receive. So there could be stuff on the front. Sometimes, like an address of where is this packet going, it could be considerably more than a single bit. Then maybe your data. At the end, there might be things to say, hey, I got the data. Did you get the data? Yeah, I got the data. Various acknowledgments that sort of confirm, hey, I'm done transmitting now. And then often, here labeled as parity, there will be some form of error correction. The absolute simplest form of that is you count up all of the bits that are on, that are 1 in your data. And maybe there's an even number of those. And if so, you'd set the single parity bit to be high. And if there's an odd number of ones, you'd set the single parity bit to be low. If the data was corrupted somehow along the way and 1 bit flipped from a 0 to a 1 or from 1 to a 0, that would change the number of even and odd bits. And you could tell because the parity bit would now not agree with the data. That is the world's simplest form of error detection, and it takes only 1 bit. There is an entire field of electrical engineering which deals with error detection and error correction codes. They take more and more room because you're putting more and more data in the slot that says parity there, but they can, in some cases, actually not just detect that an error has been made, but they can correct the data and they can bring it back. It seems like that's a loss because you're spending more and more of your time transmitting this error correction. But it turns out when you do that, you can then run the system a lot faster. And if you can run it faster than the amount of loss you got from adding these extra bits, then overall that's a win. So that's a very common thing in communication. We won't have to worry about in this class, but just so you know it's there. The point is, you get a certain number of bits that you're transmitting. Wrapped around it in the frame are all these other things. And that's overhead that doesn't contribute to the rate you actually care about. The last term that we need here is a term called baud, B-A-U-D. If you've programmed your Arduino already and talked to the serial monitor, that also is a serial communication format, you've used this. Baud is bits per second. Baud is the same as hertz, but it's basically the digital version of that. And it would say every one of these bits is coming at you how fast. 9600 baud is a pretty common value for our low-speed Arduinos, and that means every one of these bits is coming at you 9600 per second. And notice that means you don't get 9600 data bits per second because you have to transmit the whole frame. So that's enough to give you just a little idea of when you say send a character or a number across a digital serial communication format, every byte is wrapped up in something like this and shipped out the serial port. And if you really care about how fast that's going, how rapidly you're getting data, you need to understand a little bit about this overhead that's put on the frame.